Cool. Thank you. Pleasure to welcome TRG, who is going to tell us about Landau Yang theorem and its generalizations.
Thank you. Thank you, Ranju, for this nice invitation. I was actually passing by from Canada. I thought I'll drop in Dublin and then go back to Chennai. So next week, after 4 days, I'm going. I thought I'll come and meet people and probably give a talk. So with that, I'll start what I'm going to say. This is actually something inspired. I specifically wanted to give this talk because there is an emotional issue about it. This is some issue on which Professor Balachandran and myself, we had a lot of discussions. And we had done areas of work, and I was inspired by discussions with him, and we published the paper, not with him, but with another collaborator. He has done several. So I thought I will at least dedicate this talk to him in the place where he has been always associated. And it's a great honor, at least for me. Okay, so the plan of my talk is to tell for general thing what is Landau Yang theorem, and I'll give very simple proof of that. So the theorem is so simple, the proof is also very simple. Then I'll go a little bit about Poincare group representation theory, which is used in all monofield theories. And the generalizations which I want to do are 3, 4, and completely conclude in the last one. So this is going to be my scheme of things. And what is the Landau Yang theorem? In 1949, Landau posed a selection rule. It's essentially a selection rule that a massive spin 1 particle cannot decay to 2 massless photons. This is the simple theorem. And this is in 1949, and that's the reference for that. In 1950, Yang made a similar rule independently, because in those days, the connection between Soviet Union and the rest of it took a lot of time. Even though the work is almost the same, similar, and it was done in 1950 by Yang. And that is the reference for Yang's work. Now, these statements are now known as Landau Yang theorem. The elegance of the theorem is you don't need any Lagrangian action, nothing is needed. It's only Poincare group representation theory is needed. We need a symmetry which is coming from Poincare group. That's all that is there. And secondly, we need one more. These photons are bosons. Photons are bosons. So we need the Bose symmetry also. There is a symmetry of the 2 particles which are going to be emitted. So that is the only thing that is needed. Whatever is your action, renormalizable, non-renormalizable, anything you take, this, as long as the theory obeys Poincare group, with this thing it will come out. Okay, so what are its implications? Before giving the simple proof, it has nice implications. For example, there is an electroweak Z particle is there, Z boson is there. It cannot decay to 2 photons because Z boson is massive, and it cannot decay to 2 massless photons. That is the first result. The other practical thing is rho meson, which has spin 1, does not decay to 2 photons. Whereas a pion, which is a scalar, okay, spin 0, and it does decay to 2 photons. Now, recently, this theorem is applied in the Higgs boson. Higgs boson, we don't know whether it is the experimentally LHC finds the boson with some mass 125 GeV. But are we sure it is a spin 1 particle or a spin 0 particle? That's the question. And interestingly, it was found to decay to 2 photons. So it cannot be a spin 1 particle if the theorem is true. So now this is basically the set of implications which I can list, and it shows that it's a very nice result. It is so general that it can be used. Now it is very easy to show. We will first prove the theorem using simple arguments. Then we will prove the same theorem using Poincare group representation theory, because then after that I can go to the generalizations.
I have a question.
Yes.
We know that Higgs boson can't be a spin 2 particle.
Spin one part. It cannot.
Spin 2.
No, spin two.
Spin 2.
I think that also will be rolled out in this example. But I have not worked through that part. I've only bothered about spin 1 and spin 0, but my guess is it cannot be lost. Okay. Without losing generality, I'm going to assume massive spin 1 particle. We can take it to be at rest. So the 4 momentum will be m0000, it's at rest. And in addition to being at rest, it has a spin vector associated with that, which I will call as a capital S vector. So that is as well as particle which we are going to look for its decay. The massless photons will have 4 momenta. So, but only thing is, by momentum conservation, the 3 momentum should go in the opposite direction, because you start with rest other this thing. And they are k and minus k. And since they have the k and minus k and massless, the energy will be mod k. That's what is it. So the 3 momenta are k and minus k. In order to conserve the momentum, the polarization of these 2 photons will be in the plane perpendicular to k. That is the thing. K, if it is in a particular direction, the polarization will be in that plane perpendicular to that. Okay, so we label the polarizations as other 2 vectors S1 and S2. And since they are all perpendicular to the k vector, I can take it with k dot S1 is equal to 0, k dot S2 is equal to 0. Now we have several options. We have k, S, S1, S2. These are the vectors which are available to you. You write all possible combinations in which this amplitude can be written down. Now, there are 3 generic terms that can be written as candidates for the amplitudes. The first term is S dot K, S1 dot S2, because all of them have to be S and S1, S2 have to be linear. So you can have S dot K, S1 dot S2, or you can have S1 cross S2 dot S, that is one more thing, with the K part of it goes into the constant in front of it. And the last one will be S1 cross S2 dot K times S dot K. This is the only thing that can be written down. There is nothing else that can be written down. These are the 3 amplitudes which we can write down.
Why can't you have higher powers of S?
What is it?
Everything there is linear in capital S.
Yes.
So why can't you have capital S dot K squared?
Yes, yes with K square. K squares are already included in the quotient.
S dot K.
S dot K.
That's a linear factor, isn't it?
Yeah.
Yeah, but couldn't you have the square of that factor?
That will be written again in terms of K square. It will go into the A3, K square, etc. That
No,
so there is nothing more that can be written down by general arguments.
why not?
I
don't see why you can't.
Because there is only one S which is coming S1, S2,
Doesn't matter.
right? Now what is happening inside is inside the diagrams. In fact, I will be writing down the diagram first. This is the only thing that is possible. There is nothing else that is. But anyhow, it will be proven by even Poincare group representation.
I don't see that.
Well, you are asking whether S dot K whole square can be there. Is that the idea? Now the K has to be one linear in all these things. K has to, apart from the K squares, which are Lorentz invariant quantities which are coming in the first part. There cannot be more than that. let me just proceed. I'll come back to this if you want.
Can I just ask another question?
Yes.
K is the momentum, 4 momentum, or the 3 momentum.
K is a 3 moment.
Okay, but you see, in the A1 of K squared there, it's like 4 momentum.
Well, I'm a bit little careless about that. That is all.
Okay, those are all 3 momentum.
Yeah. Okay. Now the general amplitude is a linear combination of them. AI K square, yeah. And AI K square are arbitrary invariant functions. The Bose symmetry of the photons imply K going to minus K along with the interchange of S1 and S2. And S1 and S2 has to be interchanged along with K going to minus K. Now we can easily check that in all these 3 terms, AI K minus K S2 S1 is minus of AI K S1 S2 S. That's the only thing. All of them obey this relation. And we should have, due to Bose symmetry, if you have Bose symmetry, under this exchange, we should have both the amplitudes to be equal. But the total is minus of that, which implies this amplitude is 0. This is a simple proof, which more or less what Landau gave. And of course, in a specific context, Yang also used it to prove that rho meson cannot decay. So this is the kind of a result. So this is the.
But in that case, TRT, you didn't need the other bit. You could just have used this proof. You know my question before, that's irrelevant now because you didn't need to use it. So you could have not put that down.
Well, probably yeah. You can K going to minus K, that will also work.
K going to minus K and interchange of S1, S2. It's all needed.
You don't need prop, but I don't think even that term is possible. Let me go
I
ahead.
don't think you need it.
Yeah.
All you need is that it's all
Okay. So the above theorem does not depend on the details of the action or the nature of the discrete transformation property, whether it is CP or C or P, all those things are not needed, or the initial vector particle. We see that the above theorem stems only from the properties of Poincare group, because that's what I have used. And secondly, the Bose symmetry. Now, we can argue the same theorem if that's what was done by Majorana and Joe several years before, and that's what I'll describe it the next. Irreducible representations of the Poincare group. Now, if you take Poincare group, there are 2 invariants for that, which are corresponding to the mass and spin of the particle. And those invariants are P mu, and Pauli-Lubansky vector. But if it is massless particle, there is only helicity for it. Mass is 0. Helicity is the only thing that will go with that. And I will not worry about other representations which are I'm not using it here.
But can I ask another question?
Yes.
I just want to keep going. Ask some questions. In the first, simple proof, which preceded this, where did we use or where did you use the masslessness of the decay states?
Yeah, that
Where did that come in?
it has only helicity, and the helicity is an invariant.
Yeah, but
So K dot S1.
where did it come in the non-complex?
In the theorem, K dot S1 is 0, K dot S2. That is it.
Oh, yeah, okay.
That is it.
And you wrote the argument down for any spin S.
Yeah, I'm good.
So
Right.
it says that any spin,
I'll come to that. Now, I said spin 1.
you didn't show anything for light on spin.
Well, actually, I have said mass is spin 1.
Would you?
Now, it can here, the spin can be anything higher as of now, but what Balacharan showed is for spin 1.
But if you go back to your previous ones, where did the argument rely on it being spin 1 before this? Didn't use it.
Well, I in principle did not use it. That's true.
You
But
just wrote that
six,
S,
yeah.
minus spin.
Yeah. But the spin greater than 1, like spin 2, etc., will have magnetic quantum numbers plus 2 and other things. And there is nothing which can come from massless photons of that type. That's what. See, massless photon maximum it can go only to 2 plus 2. That is the only thing that is also ruled out. There is nothing we have to. Actually, in principle, we have to worry only about maximum spin 2. Okay. The Poincare group representation is generated by this P mu, M mu, nu, and the translations and Lorentz group generators. And Casimir invariants are P square, P mu, and W square, where W mu is the Pauli-Lubansky vector, which is given here epsilon mu rho sigma, P mu m rho sigma. W square is the thing. When P square is equal to M square, which is greater than 0, we get irreducible massive representations depending on the value of W square. For P square is equal to 0, we get massless representations, and only thing is we need helicity. What is the value of the helicity? That is to be given by that. These results follow from the induced representations of the little group, which is what Wigner and others worked it out some several decades before. I'll explain that part slightly later. For the massless particles, the force momentum is P mu with omega 0, 0. Earlier I wrote it as K, but omega 0, 0, K. And the little group, which will leave the vector invariant, is E2. That is the group which will leave this vector invariant under Lorentz group transformations. And the little group for massive particle is SO3. So these are the characteristic difference between massive and massless particles. And this plays a crucial role in all these examples. Now, the SO3 is very easy to see because M 0, 0, 0, you can move any rotation in that 0 vector and you will not change that. Okay. Actually, but we want to describe our photon by the electromagnetic field, which is A mu, okay? And it has two helicities, not one helicity, which is plus or minus 1. So you can ask that question whether that A mu represents, it's a side remark. That part is a side remark. A mu has, actually it's a reducible representation. It has both plus 1 and minus 1 helicity. And the interesting thing is, even though it is reducible, but it is not decomposable. This is something which was known. In fact, that person I advertising is happens to be my advisor. P.M. Matthews is the advisor, and he was the one who did this work. That the electromagnetic work. This is where the origin of when you try to quantize it. There are a lot of complications arise in even free field quantization, etc., because of this indecomposability of the vector field. But it is nothing specifically related to our work. Okay, we need to look at the content of the product of two massless particles, which is helicity plus or minus 1 representations. You are going to take the direct product of such representation and see whether spin 1 particle is there in that representation. Secondly, it should have Bose symmetry. Bose symmetry. That's what is the thing. So the direct product of representations can be easily assigned by the Clebsch-Gordon coefficients. And we should impose the Bose symmetry. So the demand that the symmetric product of two massless representations of the Poincare group should contain a spin 1, massive spin 1 representation is the demand. And that's what Balachandran and co prove that it is not there. That's what is the. It was done in 2007, and the direct product of two massless representations with 4 momenta P 00 plus or minus P and helicities lambda 1 and lambda 2 is very easy to write down because we are going to use the SU2 representations, SU2, and the matrices are dj mu lambda 1 minus lambda 2, and these I, which are writing on measure, is a hard measure of SU2. So this is the kind of a thing which you are going to take the product, which I have written down the product. And the product to identical particles, we have, this is the way in which the Clebsch-Gordon coefficients are very easy to write down. In this case, which what Bal and Co have written, and the crucial thing is it is plus or minus 1, j plus lambda 1 plus lambda 2. That is the way in which those things will combine. For photons obeying Bose statistics, we need the symmetric product. For the symmetric product with two identical particles of helicities, which is lambda I is the plus or minus 1, and lambda 1 is actually plus or minus lambda 2. That's what is the. And if I write down the symmetric product, the result will be equation 6, which is what you will have, and that is 1 plus or minus 1 to the power j plus lambda 1 plus lambda 2. So this is a simple Klebsch-Gordon theory result of product of representations, which those people wrote down. And now we can ask the question with j is equal to 1, and the right hand side vanishes. The right hand side vanishes. This implies the two photon states cannot have j is equal to 1 component, thereby forbidding, for example, j is equal to z going to 2 gamma. Is it going to 2 gamma? So this is the, and many others. On the other hand, if j is equal to 0, we expect for the Higgs, the decay to 2 photons is not prohibited. And if I put j is equal to 2 also, it will be prohibited. That's what is that. It's not, this is the thing, and that explains the scalar nature of the Higgs. Okay. Now I'm coming to certain ways in which you can avoid or evade Landau Yang theory. And then generalization also I will point out. The question of mass of the photon was raised by Schrödinger himself in 1955 in this institute. There is a very nice paper by him, Bose and okay, I'm not given the reference, but Bose and Schrödinger, which asks the question: must the photon mass be zero? Must the photon be massless? That is the question he asked, and he answered: you can have a very, very tiny mass. You can have very, very tiny mass for the photon, as long as the photon interacts with the matter only through a conserved current, J mu mu, where the J mu is conserved. And the answer is because L interaction is J mu mu. Now, the basic idea is if J mu is 0, and if the action is integral J mu, there will be 3 components for the, if it has mass, for example, if vector field has a mass, it will have 3 components. It will have a longitudinal component also. And that longitudinal component will typically of the form d mu phi. So you will have J mu d mu phi, and integral by parts will give you d mu J mu. So only the surface terms will contribute. And the surface term, what I mean by that is in a scale of 1 over m, Compton wavelength, if mass is very, very tiny, like 10 power minus 20 electron volt or 10 power minus 18 electron volt, that length scale turns out to be of the order of light years or 100 light years, etc. We don't have to worry about it. So this is basically the idea. And in his paper, it mentions very interestingly this remark: even if we find in nature the limiting case is realized, we should still feel the urge to adumbrate a theory which agrees with experience on approaching to that limit, not by a sudden. This is a very interesting.
Something wrong with the English there. You can't take the first not by a sudden.
What is it?
There's something wrong with the English there. You can't say not by a sudden.
We should still, which agrees with experience on approaching not by.
Maybe not all of a sudden.
All of us. Okay.
The other thing
This
is
is actually taken from his thing. I copied. I might have made a mistake.
well, I don't know whether Schrödinger wrote in English or German, but the other thing is that nobody would expect the conserved current to be conserved if you had a small mass. I would think.
Conserved, why should J mu current to the electron be not conserved?
Well, I think it should be conserved.
Yeah. Huh? It should be conserved.
Yeah.
So it is conserved.
But if there was a massive photon, I wouldn't expect it.
Why do you expect it to be not conserved?
It just,
For example, with W boson, various particles are coupled.
yeah, but then,
They're all having conserved currents.
well, that's a very difficult question which wasn't solved for a long time.
No, it is in principle that's the way, for example, before this name,
The electric weak theory is really a massless theory in disguise, and the triumph of spontaneous signature written. But as if you get masses, there's nothing happening like that.
But it happens here also. For example, this work of Stueckelberg and also later Abelian Higgs mechanism It's a limit of that is you can have the mass of the photon going to zero. So when you have a Abelian gauge field like U1 gauge field coupled to a complex gauge field, there will be fixed part and a phase part of it.
Yeah, but you see, the problem is that if you've got a mass,
Mm.
and you're not got a mass, there's a dimensional parameter present in one, is not present in the other. So I think the two things are very different.
So, but even in Abelian mechanism, the current is always conserved. Am I making a mistake?
I think
It's that kind of a limit. He essentially thought of as a Poincare theory when he wrote the paper, 1955. When he wrote the paper, he gave only Poincare theory. He was more or less concerned with if photon has 3 degrees of freedom, whereas if you do black body radiation, we find the number of modes are multiplied by a factor of 2. And from there we get the Stefan's constant. Now, if he asked the question, should I multiply by 3? Answer is we should not multiply by 3 as long as this current is conserved. Now, it so happens in QED, because of the infrared problems and other issues, Tom Banks, when he writes his quantum field theory book, he uses only massive QED, where the photon is massive, which is very, very tiny mass. And all experimental results will not show any difference as long as the massive. They will be corrected by the order of n square. And if m is very, very tiny, you will not find any difference. In fact, that's what the whole book is about. He wanted to avoid discussions about infrared questions. Okay. Now the estimate on the bond of the mass of the photon was made by Schrödinger himself. He considered the earth as a magnet. And then from there, if it is a magnet, it should go like 1 by r cube or 1 by r square potential. And from there, you can estimate by knowing the magnetic field on the surface of the earth at several places. And he put a limit which is 10 power minus 16 electron. It should be less than that. Of course, it is a limit, it should be less than that, it can be as good as 0. That's what is the thing. Now, people have done much better geophysics, magnetic field results, which was Goldhaber and Miatu, if I'm right. And that this is the limit as of now, which is there in particle data book, which is 10 power minus 18 electron, as of now. And for all particle physics experiments is as good as 0. Okay, it is obvious that if photons have a small mass, the question of the representation theory of the Poincare group takes a new angle. If it is a massive one with small mass, the representation theory which I used earlier will have the E2 will not come, it's only again SO3 will be there. It becomes a question of whether in the tensor product of 2 massive spin 1 representation, photons, obeying Bose symmetry, is there a massive spin 1 representation? Is there? The answer is obviously yes. Now you have the third component playing the role. This possibility arises because massive photons have 3 degrees of freedom, including the longitudinal photons. It gives a longitudinal component to the polarization SI, a new term, and the important thing is K dot SI is not 0. It is no longer 0. So that is the difference. So there is a new term which appears, and that term is S1 cross S2 dot S cross K. Okay. Now we can write it in terms of K dot S1 and K dot S2 by simply product rule of 4 vectors like this, which is essentially the change which appears. And this term A4 is a term which is the issue of, will produce a new contribution. It will produce a new contribution. I will explain at least the order of magnitude, what will be the contribution. Now the question of mass going to 0 limit can be posed as a group theory question, which was done by, again, Wigner along with Inanu, which is called Inanu-Wigner contraction, where SO3 going to E2. Now, SO3 generators are L plus minus L3, which is the equation number 9, which is the conventional SU2. Okay. The group is E2 is specified by Px, Py, and L3, and they obey the equation number 10. The question is there a transformation from here by a one parameter transformation from L plus minus 2 px py? Okay, that is the question. And the answer was given by Inanu and Wigner, and that is its transformation. Px comma y is S inverse Lx y with S, where S is a matrix which is 1, 1 R, with some R is the Compton wavelength if you want to say that. And the limit of 1 over R going to 0, we get the SE2 group. This is the famous Inano-Wigner contraction. It is there. Now I am talking mainly about SO3E2, but SO3 is a subgroup of Lorentz group. So also E2 is a subgroup of A, but we should put everything in the same group. Now there are two groups here, but in the real case of for our problem, we should put it in that way. Okay. This was escalated to Poincare group itself, or Lorentz group versus Poincare group, by Kim and Wigner in 1987. Both SO3 and E2 are subgroups of Lorentz group, SL2C, and you can escalate it to the same group, and that escalation is what I have written down. For that, we should see the E2 part of SL2C, and the E2 part, the SL2C has 6 generators, J1, J2, J3, and K1, K2, K3, corresponding to rotations and boosts. And you write down N1, N2 in that way. So the Euclidean group is given by J3, N1, N2. And this transformation will give you the details about in the Lorentz group itself, how you can do the the Inano-Wigner contraction, which is the basic idea about it. So this is the, you can say it is some kind of a covariant way of describing the whole thing. This is actually a side result. Okay, now coming to the generalizations. And the generalizations are the extension of the above theorem, first of all, Landau Yang theorem. I'm not going to massive particles, but massless particles. I will generalize it to supersymmetric context. In the supersymmetric construct, there is again super Poincare group, and the super Poincare algebra again has two Casimir invariants, two operators, and the p mu which you had earlier continues to be the invariant quantity operator, and that is the mass. And the second thing is a generalization of Pauli-Lubansky vector, which is called the superspin operator, which commutes with all the generators. So the two generators are the mass M, the superspin operator Y provides a massive irreducible representations of the supersymmetry. Okay, in the case of supersymmetry, when Y is equal to 0, we get the supersymmetric multiplet, which is scalar field and a spin half field, which is a Majorana particle. And the vector multiplet consists of Y is equal to half, in that case, massive vector particle Z and two chiral spinors, xenos. You can call it xeno 1, xeno 2, and scalar phi. This is the way the combinations of these things appear. On the other hand, the massless representation has only gamma, which is a photon, and its partner, which is a Majorana partner, which is photino. Photon and photino are the two things which will form a massless representation of a supersymmetric multiplet. Given the thing, we can easily see the extension of the Landau Yang theorem. So what is the thing is, Z going to 2 gamma will again be prohibited because Poincare group is there. Now the only thing is that Z which is appearing is part of a superfield and coming from the vector multiplet, whereas the gamma is coming from a part of the massless representation, which is photon and photino. And the interesting result which comes out, if superfield notation, if you write for Z gamma gamma, and we say that such an amplitude can never come, it will prohibit all the terms which are associated with it. And those other terms are, very interestingly, the Z gamma gamma as external legs with superfields are prohibited, then it will say that Z photon cannot go to two photinos now. Instead of two photons, you can say it will not go to two photinos. Two photinos are actually the Majorana particles, massless Majorana particles. Z cannot decay to two photinos. Hence, but only thing is the photons obey Bose symmetry, whereas the photinos obey the Fermi symmetry. So now with the Fermi symmetry, Z cannot go to two photinos. That is the new result which will come from this. And very interestingly, such a decay is prohibited even without going to supersymmetry by Poincare group itself, using the earlier Balachandran-Jo's theorem. And if I put whether the spin half there, massless spin half particles, Majorana particles, then that term which I have written down earlier in that equation 6 is identically 0. It will actually turn out to be 0. So that's an interesting result. But only thing is, if you have a photon which is massless and a Majorana which is massless, there will be automatically a supersymmetry which will be always present as free particles when I try to write down the action. Okay. So now the interesting thing is, now the Z cannot go to two photinos, which is what I have written as F and F bar. That is the diagram A. A decay of Z to two massless Majorana fermions. Okay. But the interesting thing is, I told you that Z, gamma, gamma superfields will not be present, which means all other terms which are associated with them are also not present, which is essentially the super partner of Z, which is Zeno, cannot decay to a photon and photine. A super partner of Z, Z tilde, which I have written down, cannot go to photino, which is gamma tilde, and gamma. That term is also 0. Okay. Now the interesting thing is there is no Bose symmetry or Fermi symmetry here, but only thing is there is a supersymmetry which is needed for this term. With supersymmetry, we will even find such term is 0. Okay. This is in spite of the fact that all the three particles are distinct, and only representation theory of super Poincare algebra, along with the symmetric antisymmetric product of irreducible representations, whatever Ball et al. Done, should be escalated to supersymmetric theories, and that will give you the powerful result. So this is the kind of generalization which is there simply from Poincare group. Now, only thing is, if I want to claim Z cannot go to 2 gamma, etc., I have to now look at the Weinberg-Salon model itself, and there we can consider a massive photon by what is called Stueckelberg expansion, and the extension of the theorem of the SU2 cross U1, that U1y has a mass which is given by Stueckelberg theorem. You can even put a Higgs mechanism for that. So we have written down explicitly to do the calculation that such a term with massive photon is allowed, and what is its value. And that actually has to be used. There is a very interesting review on Stueckelberg theory by people, and I'll give you, this is a reference, and this is the kind of a term that will be needed for. So the kind of a triangle diagram with gamma and gamma, and we can compute for such a thing what happens to the, exactly what happens to the amplitude. And that is a very long calculation. I don't want to bore you with that kind of integrals, etc. Formally, I will write down that integral in this form: gamma mu into 1 minus gamma pi by 2 by C1 gamma lambda by C2 gamma mu by C3, where C1, C2, C3 are the propagators which are appearing here. And we can do this thing, we can do this calculation and find the estimate. What is required is the estimate, and that estimate will turn out to be proportional to the mass of the Z particle square. And the first two terms are the coupling constants, which we can ignore. It will be proportional to the mass of the Z particle, and it will be proportional to the mass of the photon which is there, along with mass of the electron, I consider the loop to be electron also. I consider the loop is made up of electrons. In principle, you can have muons and tau also. They produce even much less contribution. So this is basically the contribution that will be there, and this is non-zero. If m gamma is non-zero, the answer is non-zero. If m gamma is zero, whether it is supersymmetric or non-supersymmetric or what is, I think it is always zero. So this is basically the idea. In the above expression, mz, me, m gamma are the masses of Z boson, electron, and photon. And you find that m gamma going to 0, Z going to gamma, gamma is prohibited. And we do have such a non-zero value. And when we have a non-zero value, how does it come? So the two photons are there. One of them can be a transverse photon. Another one has to have a larger component of the longitudinal component. Longitudinal component plays a crucial role, and that is what is producing you the extra term of the order of m gamma square. So this is the kind of a thing. Now the question is, can you experimentally find longitudinal photon? Transverse photons will ionize because they interact with matter and produce, but the longitudinal photon, which is there, so you have Z going to a transverse photon and a longitudinal photon, which you don't see. Where can I see? Is the only way I can see is missing momentum, missing energy. In some sense, somewhat similar to what neutrino, the proposal initially came, that there is a need for one more particle, which is almost massless at that time at least. And if you want to see that, you should see missing momentum and missing energy. And that's the kind of a thing that will happen. Okay. Observing longitudinal photon itself is very difficult as its interaction with matter is very, very small. The only option is missing energy and missing momentum carried by it. In spite of the observational difficulties, a non-zero photon mass, however small it is, by escaping Landau Yang theorem without breaking Lorentz or Poincare symmetry, has been used. Okay. We can extend the above to the supersymmetric case also. I did the Weinberg-Salom model without supersymmetry. One can do with supersymmetry also. Prannath and others have been doing a lot of these things. And one can extend this kind of a model to such cases. Okay. Such extensions of Stueckelberg QED have been done, and that is what Prannath et al. Have done. Landau Yang theorem is an important selection rule which has helped in understanding the role of symmetries in particle physics. Hence, here we have extended prohibiting the decay of spin 1 particle to Majorana particle also. It provides a link to SUSY generalization. Okay, while the theorem can be evaded through breaking of Lorentz symmetry, people have considered, why should I have Lorentz symmetry? I can break it. Then you can do that, but then the scale of that will come, but that looks slightly unpleasant. So I didn't take that kind of a view. While experimentally, the deviation will depend on the mass of the particle, and which will be extremely small. Actually, the role of mass of the particle can be understood by the last thing which I have written down. Now, is that the process that going to 2 gamma can be written by this interaction in a gauge invariant way. I'm writing everything in a gauge invariant way, which is F nu rho, F nu sigma, G rho sigma, along with d mu v nu, where d mu v nu is the massive particle. So the two photons couple. This is the interaction term I can write down. Now this interaction term, by integrating by parts, it will be 0 because d mu f nu is 0 on shell. Now if d mu f nu is not 0, it's proportional to a nu, then it will produce a non-zero result. So the mass of the photon can play a role is what you get from that kind of a thing. Similar thing can be obtained for the supersymmetric case also. So finally, I conclude. This is based on our paper with Rakesh Tibrewala, which is appeared in JHEP few months back. And as I told you, this is a kind of a dedication I want to tell about Balachandran's collaboration and interactions with me for the past 4 decades, several decades. And he has been inspiring me for all the work that I have done, many work which I have done. And even though many of them he didn't collaborate, I used to discuss with him on all my work. And this is for him. I'm not going to see him hereafter. Thank you. Thank you.
No, you said that the paper of Pal and Joe also shows that the spin bond can't decay into Majorana particles. So where does the Majorana property play a role? So I infer from that it couldn't decay into a normal film, but that wouldn't work.
If it is massless particle, representation is automatically Majorana. Well, there will be two fermions. Otherwise, if you have a well fermion, if the massless limit, okay, the massless limit, it will be reducible representation. That's what I'm saying.
So just wondering why people didn't point that out since they were thinking about Bose statistics. Why didn't they just?
I don't know. In fact, that's what. In fact, it so happened that I was doing from supersymmetry. I had discussions with Bal. Then Bal went back to his book and paper and said, "Oh, you don't need supersymmetry." And he actually fought with me. You don't need supersymmetry. Without that, I can prove it. Yes, sir, I agree with you. Your paper has that thing. But this is the thing which the other one where Zeno cannot go to photon and photino is also interesting. So it looks from that point of view a new result. We agree that it's a new result, new way of thinking, but no one has actually claimed. That's what I say. In the result cannot go to two photinos. I don't think anyone has claimed, even though you can make a remark from this. But as I told you, if you have a photon which is massless and a photino which is massless, it will automatically have as a free theory supersymmetry. It will also inbuilt into it. But the full theory may not have.
I didn't completely understand the way you described the Wigner inaugural contraction. You were relying on some dimensionless parameter R. But where do you get that dimensionless
Well,
parameter?
R is a dimensional parameter, which is the radius. It's almost like, see, when we have SO3.
No, I understand the dimensional, but I need a dimensionless parameter from that.
Okay, so the dimensionless parameter, if you want to have, you should put it as M over R.
You described it, you've got one R. So there's
Yeah.
a dimensionless parameter in there.
Yeah, I should put with the mass term also in it. That is the way it is. It should be taught as a that M is something like M or H by MC, which is my content wavelength, and that's what should play the role.
So it's a momentum dependent statement.
Well, actually, it's not a momentum statement because it's like mass of the particle is a Lagrangian invariant state.
The massive particle is already scenario state, yes.
It's a massive, that's why I wanted to put everything in a covariant way. That's what Kim and Wigner did.
That's
so.
R dependent. One of the equations you wrote down are dependent on a ratio of velocities, which is dimensions, but you also have a log of R.
Yeah. No,
You're saying R is dimensional.
that part is taken essentially from Kim and Wigner. They were trying to find out SO3 as a subgroup of SL2C and E2 as a subgroup of L. How do I go in the representation theory sense now? Because it's the same group. The representations coming, massive representation go to massless representation in a contraction way. That's what they were trying to add. That's the interesting part. Very interesting, it was done around 1989. People didn't ask that question at all. Because people knew SO3 going to E2 even earlier. Yes. That contraction is known. But the only thing is, we want both SO3 and E2 as part of Lorentz group, and one representation which is coming from massive representation going to massless representations. That's what is the. So that's a slight twist in the calculations. So done around 1989, right?
May I ask a question? Thank you so much, Theurgy, for the very nice talk and for dedicating to Bal.
Yes.
I wanted to ask, so my connection was unstable, so I missed little bits here and there. So I do apologize if you've mentioned this before, but could you clarify whether the Zeno to photon photino amplitude would still, the vanishing of this amplitude, would it still hold if there is soft SUSY breaking terms?
If there is soft SUSY breaking, that will not hold. That
see.
will not hold. But you still have Poincare symmetry.
Yes.
But soft supersymmetry is broken by maybe some mass term for something, etc.
Yeah.
And there is probably a term that can be written down to allow Zeno going to photon and photino.
Okay. So it does depend on how you break the SUSY.
Break the supersymmetry.
Okay. Thank you very much.
Thank you. Is it okay?
Yeah, I'm just trying to get the two scales that we were video.
Yeah, this is a problem of when we put all the H bar going to one, C going to one, C limits, etc.
No, I don't think so. I think it is, I think that it's a multiple. It may. You have a massless photon, and you have a massive photon, and you want to.
Go to, see, I'm going to zero limit. Well, actually,
I think there must be a momentum dependence in the.
There is, it's like a soft pion theorem, you know, pion that used to be in the literature. So we're having a soft photon theorem.
Yeah, well, if.
There are soft photon theorems. Infrared problems come from.
Yeah, no, just the way he described it, I know how Wigner neural contractions work.
Yes.
I know.
Yeah, there's a parameter which is dimensionless. I agree with you.
Right.
I should be able to put it with that thing. See, within the framework of SO3 to E2, there is no problem. I can write. Even though
It's a triviality, you know how to do it.
Yeah.
Yeah,
but I
just
put it
one
in.
of the generators has to scale differently
Yeah.
to the other.
Yeah, it's essentially one of the sphere on which SO3, that S3.
Geometrically, it's clear.
Yeah, so it goes to infinity and then
Physically, what is setting the ratio there is. I suspect that there's the ratio of the mass and the momentum is coming into it. Which,
are you saying that it will break Lorentz invariance? That's what I'm wondering. I don't think there is a Lorentz invariance break.
Either way you've set it up, to do the contraction, you must break the Lorentz invariance. To set it up that way, to view it as a contraction, because the limit is has.
For example, I didn't do in the case of because I needed a really physical spin one particle for being the Z massive particle. Z served that purpose, so that's why I went to Weng-Basala model. Then I did the same calculation with the thing, and there is no Lorentz invariance breaking. So
No, there isn't Lorentz invariance. You're right.
Yeah.
I can do it with projectors onto the longitudinal and the transverse.
Precisely.
And it's.
So in that
It's
limit, the
that-
longitudinal and transverse components decouple. It's kind of entanglement of these two particles.
Yeah.
They get decoupled. That's what is happening.
So
That limit
So it's physically what's setting the ratio of the two projectors.
is a combination of these two things which can make the states. That is what is the thing. It's actually something which is mathematically interesting to resolve.
Yeah.
Which I actually, I must apologize, I didn't make that point a little better. I should go through it again. Thank you.
You were getting a limit on the photon mass based on Earth magnetic fields. Are there any stronger constraints coming from astrophysics or cosmology?
Precisely. It's good that you asked, which is what I've been doing. One is there is a third component, which you can call as a Stueckelberg field, separate field. And the transverse component and this in a length scale of 1/m, they are decoupled. And the third component does not interact with any matter. The interaction is not there. It's only transverse component interact in the scale. So the question is, if all particle physics experiments will not show the difference in all our landscapes, but they also have, the third component also has mass and also energy. So they play a role in gravitational physics. Now, the question which I asked, which I've been asking and also produce some results on that, is can it serve the question of dark matter? The Stueckelberg field, can it be, it's like axion-like dark matter. It's like axion, extremely small mass, 10 power minus 20 electron volt or minus 22 electron volt. Scalar particle is there. Can it play the role of dark matter? That is the question. And such dark matter is called fuzzy dark matter in the cosmology side. And there seem to be some good theoretical backing for such fuzzy dark matter. Phenomenologically, there are some interesting things because such dark matter with extremely small mass can play a dark matter role only because they will all travel with the velocity of within quote light. So they will disperse from this thing, but it has to be held inside. In order to do that, they should form Bose-Einstein condensate. Now, the Bose-Einstein condensate, interestingly, will depend on what is the mass of the bosons. If the mass of the bosons are tiny, like 10 power minus 20 electron volt, the critical temperature at which condensate can be formed will go like 1 over m to the power 1/3 or something. M to the power 1/3. So the critical temperature will turn out to be on the order of Big Bang temperature, 10 power 17 degrees Kelvin, 18 degrees Kelvin. So if dark matter is formed and they form a condensate at that time, they will remain condensate for all times because the temperature has been going down. So the condensate formation is crucial. So there are some practical way in which phenomenologically that seems to agree, because the quantum wavelength of such particles, like photon, this in the third component, will set the scale of the dark matter condensate which you have. So you can, one simple question you can ask is, what is the smallest galaxy you can ever find? The smallest galaxy cannot be less than the quantum wavelength of this mass. That is the hand-waving simple argument. And that gives me, with the 10 power minus 22 electron volt for this, gives me something like 100 light years. That is the quantum wavelength, 100 light years. So experimentally, people have discovered a lot of dwarf galaxies. All of them have size of radius or something like that, or of the order of 200 light years, 300 light years, 1000 light years, even 100,000 light years. But the smallest galaxy is something called SIG2, and that has a value which is about 130 or 40 light years. So it seems to work within that framework of this kind. There are a couple of more, let us say, heuristic thing which will be of use, like pulsar timing array, etc., from this kind of thing. So there is a potential use, potential practical way in which we can utilize it in cosmology. In fact, I have written a couple of papers, few papers on that. I'm still working on that also. So cosmologically, it may be useful.
Could you tell this apart from axion and dark matter?
This is axion-like dark matter, not axion. Axion is ruled out as a dark matter. Axion-like, because the QCD axion which is there, that mass is not of this range. Whatever theory is demanding. So that is what it is.
But could you differentiate it from axion-like dark matter?
Yeah, it is a new particle, which is part of the particles which we know. And there are some interesting theoretical way in which one can argue about it. One experimental thing would be the issues about gravitational waves from the initial. For example, if you want to have a galaxy formed at 300 million years after the Big Bang, and that must be dark matter also at that time, and must have expanded to this, and there should be black holes also, supermassive black holes also at that time. those things can happen only within this framework of this kind of darkness. As of now, that is the argument. But I don't have very stronger than this, because I'm not a cosmologist or astronomer. I've been talking to people. What is it one can do about it? This is only a guesswork which I'm trying as of now. Thank you.
Shouldn't the temperature for the condensate go down with the mass? The dimensionless ratio is.
No, actually, it depends on the density of the dark matter. It is rho divided by m to the power 1/3. Yeah,
Yes.
that is the thing. So I take what I don't know what is the dark
So you're
matter is.
getting the rho to.
Yeah.
Okay.
So if I know the solar system in that dark matter, experimentally they claim it will be 1 proton per cc. That is a estimate which they have of the dark matter energy, or 1 GeV per cc. Now we can say that the whole solar system is filled with dark matter as a fluid, and it doesn't interact with us. It is there to us. So this kind of, interestingly, this kind of idea was talked about by John Sudarshan in 1974. It's very interesting. He did talk about the superfluid nature of dark matter. That is what is that. But anyhow, it is beyond the issues here. Okay, thank you.
Thank you very much.
Thank you.
Thank you.
Bye-bye.
Okay. If you have any question, you can always send me email.
We'll do that. You're here for another few days.